Invisible rivers flow in the emptiness between galaxies. These are not made of water, but of dark matter and superheated gas, silent currents that shape the destiny of everything we see in the night sky. By the end of this journey, you will understand how our entire cosmic home is built and guided by these hidden pathways. We will uncover how galaxies are born from these streams and why some thrive while others wither away. What invisible force could possibly choreograph the dance of billions of galaxies? How do you map a river you cannot see? What does it feel like to realize we are all riding a cosmic current? Our universe is a single, breathing entity, a cosmic metropolis connected by flowing highways. Galaxies are not lonely islands adrift in a dark ocean. They are bustling cities, fed and connected by immense, invisible rivers of matter. This is the cosmic web, the largest structure we know exists. Its primary rivers are filaments, tendrils of force and matter that stretch across billions of light years. These filaments did not appear by chance. Their story begins in the first fraction of a second after the Big Bang, in a sea of energy so hot and dense that the very concept of a particle was blurry. Here, on the smallest possible scale, quantum fluctuations created tiny ripples in the fabric of reality. These ripples were the universe's first seeds. For hundreds of millions of years, gravity worked on these seeds, pulling ever so slightly on the slightly denser patches. Imagine a single breath on a still pond, creating ripples that slowly, over eons, build into towering ocean waves. Gravity amplified those initial quantum whispers into the colossal architecture we see today. Cosmologist Dr. Carlos Frenk describes these filaments as the universe's ultimate transportation network. They are the cosmic conveyor belts, the superhighways that funnel raw material toward the intersections of the web, where galaxies and immense galaxy clusters form and grow. So what exactly flows along these cosmic rivers? The primary ingredient, the very skeleton of the web, is dark matter. This mysterious substance, which does not emit or absorb light, provides the gravitational backbone. Its pull is what carved the channels in the first place. Flowing along this dark matter skeleton is a trace amount of normal matter, mostly ionized hydrogen and helium gas, heated to millions of degrees. This is the fuel, the lifeblood that galaxies consume to build new stars and sustain their brilliant lives. Understanding this foundational structure, this cosmic conveyor belt, is the first step to mapping the unseen. Beneath every visible river lies a deep, unseen undercurrent, a force that dictates the flow of everything on the surface. This is the perfect description for dark matter's role in the cosmos. It is the profound, invisible current that shapes the entire cosmic web, a gravitational scaffolding upon which the visible universe is built. Though we cannot see it, touch it, or even directly detect it yet, we know it is there because of its immense gravitational influence. It makes up roughly 85% of all the matter in the universe, meaning everything we can see with our eyes and our most powerful telescopes. All the stars and galaxies are just a small fraction of what actually exists. Its strange properties are what allow it to form these vast, stable rivers. Dark matter is collisionless. Unlike normal matter, particles of dark matter do not bump into each other or radiate energy away. Think of two crowds of people. One crowd is made of regular people who jostle and bump, slowing each other down. This is normal matter. The other crowd is made of ghosts who simply pass through one another, flowing smoothly and without resistance. This is dark matter. This ghostly nature means dark matter does not get tangled up or lose energy, allowing it to form immense, enduring filamentary structures that persist for billions of years. Pioneering computer simulations like the Millennium Run have shown us how this works. They model the universe based only on the known laws of gravity and the initial conditions from the Big Bang. When scientists run these simulations without including dark matter, the result is a formless, uninteresting cosmos. But when they add this invisible ingredient, the entire cosmic web emerges from the calculations, with galaxies falling into place along the dark matter filaments exactly as we observe them in the real world. The simulation proves that dark matter's gravitational pull is the primary architect of the largest structures in existence. This dark backbone does not just sit there, it actively guides the fate of normal matter. The rivers of dark matter create gravitational channels like deep trenches in the fabric of space. When ordinary gas, mostly hydrogen and helium, flows into these trenches, it follows the paths laid out by the invisible scaffold. The gas is pulled along these predetermined highways, funneled toward the intersections where galaxies form and merge. The dark matter dictates where the raw materials for star formation will go, and consequently, where the bright lights of galaxies will eventually shine. We have compelling evidence for this dark backbone. One key piece comes from gravitational lensing. The immense mass of a dark matter filament warps the space around it, bending the light from galaxies behind it, much like a lens of glass bends light. By carefully mapping these subtle distortions in the shapes of distant galaxies, astronomers can trace the outline of the invisible filament causing the warp. Another clue is the peculiar motion of galaxies themselves. We observe galaxies moving in ways that cannot be explained by the gravitational pull of visible matter alone. They are clearly being tugged by the vast, unseen rivers of dark matter flowing through the cosmos. With this invisible foundation now in view, a new question emerges. What is the visible, fiery substance that flows along these gravitational channels, lighting up the cosmic web for us to see? Flowing along the invisible dark matter scaffold is a second, equally vital river. This one is made of ordinary matter, a superheated, ionized plasma so thin and diffuse it is almost a perfect vacuum by earthly standards. Yet, this tenuous gas, known as the warm-hot intergalactic medium, or the WIM, holds a profound secret. It contains more ordinary matter than all the stars and galaxies in the universe combined. For decades, cosmologists were puzzled by a cosmic accounting error. Their models of the Big Bang predicted a specific amount of normal matter, the kind that makes up you, me, and every star we see. But when they added up all the visible matter in galaxies, they found only about half of what should exist. The rest was missing. The WIM is that missing matter, the hidden reservoir of the universe's ordinary substance. It is the lifeblood suspended within the cosmic web's veins. How do you find a gas that is 1,000,000 times less dense than the air we breathe and heated to millions of degrees? You cannot see it directly. Instead, astronomers use a clever trick of light. They train powerful telescopes like Chandra and Hubble on the most brilliant beacons in the cosmos, quasars. As the intense light from a distant quasar travels across billions of light years to reach us, it passes through these filaments of the WIM. The superheated gas in the WIM absorbs very specific wavelengths of this light, leaving faint fingerprints, tiny dips in the quasar's spectrum. It is like detecting a trace of perfume in a vast, dark room by the way it subtly colors a single beam of light. The gas is heated to such incredible temperatures by the most violent events in the universe. As vast cosmic structures collapse under their own gravity, they create colossal shock waves that race through the intergalactic medium. Add to this the furious winds blowing from supermassive black holes at the centers of active galaxies, and you have a cosmic forge that superheats this diffuse gas, causing it to glow faintly in X-rays. Charting this river of fiery plasma is one of astronomy's greatest technical challenges, requiring indirect methods and the next generation of space telescopes. But its discovery completes our picture of the cosmic web's flow. This river of ordinary matter, once invisible, is the actual fuel for galactic growth. Astronomers are cosmic cartographers, drawing the maps of realms they can never visit. Their tools are not compasses and telescopes alone, but a powerful combination of observation and supercomputer simulation that allows them to trace the invisible. To understand how they map these dark rivers, think of trying to understand a city's subway system by only watching where people enter and exit the stations. You cannot see the tunnels, but by tracking the flow of people, you can infer the entire network. This is precisely what astronomers do with galaxies. One of the most powerful techniques is the Grand Spectroscopic Survey. Projects like the Sloan Digital Sky Survey have meticulously measured the positions and redshifts of millions of galaxies. Redshift tells us how fast a galaxy is moving away from us, which in turn reveals its distance. By plotting the three-dimensional locations of countless galaxies, a pattern emerges. The galaxies are not scattered randomly. They cluster along the walls of immense bubbles, and most importantly, they line up along the dark, unseen filaments of the cosmic web. The empty voids between them are truly empty. This galaxy distribution is a perfect tracer for the underlying dark matter, because where the dark matter flows, galaxies are born. Scientists use a mathematical tool called the two-point correlation function to quantify this. It measures the probability of finding two galaxies at a given distance from one another. The result consistently shows that galaxies have a strong tendency to cluster at specific scales, the exact scales predicted for the width and length of dark matter filaments. This statistical map, drawn from the light of millions of galaxies, gives us the blueprint of the cosmic web. But how do we confirm that mass is actually there in the empty spaces between the galaxies? This is where gravitational lensing becomes our most powerful tool. The mass of a dark matter filament warps the fabric of space-time around it. When light from a more distant galaxy travels through this warped region, its path bends slightly, like a straw appearing bent in a glass of water. By studying the subtle, systematic distortions in the shapes of thousands of background galaxies, astronomers can create a mass map. They can literally see the outline of the invisible filament by how it twists the light of everything behind it. It is a ghost revealing its shape by its influence on the living. For the other great river, the warm, hot intergalactic medium, astronomers employ a different set of tricks. One method relies on the kinetic Sunyaev-Zeldovich effect. As the leftover light from the Big Bang, the cosmic microwave background, journeys across the universe, it occasionally passes through a filament of that superheated gas. The energetic electrons in the WIM give a tiny energy boost to this ancient light, leaving a specific, faint imprint that specialized telescopes can, in theory, detect. It is an incredibly subtle signal, like hearing a single whisper in a roaring stadium, but it is another direct way to probe this missing matter. All of these real-world observations are constantly compared against predictions from monumental supercomputer simulations. Projects like Illustris TNG start with the initial conditions of the young universe and then apply the laws of physics to watch it evolve over billions of virtual years. The result is a simulated universe, a digital twin, where dark matter filaments and flowing rivers of gas form naturally. When our real-world maps of galaxies and lensing match the structure in the simulation, it gives us tremendous confidence that we understand the fundamental rules of cosmic construction. These are not static pictures we are creating. Every new map reveals these rivers as dynamic and ever-changing flows. These cosmic rivers are not frozen in time. They have a life story of their own, a dramatic evolution that unfolds over billions of years. Picture a river delta forming over millennia, its channels shifting and merging as sediment builds new land. Now accelerate that process to a cosmic scale where the currents are made of dark matter and the sediment is entire galaxies. This is the dynamic flow of the cosmic web. From the universe's infancy, the filaments have been growing, stretching, and merging in a grand dance choreographed by gravity. In the very beginning, the filaments were faint, tenuous threads. They were the amplified versions of those initial quantum ripples, the slightly denser regions where dark matter was just beginning to pool. For the first few billion years, gravity pulled matter in a relatively orderly fashion along these lines. This was the era of linear growth where the cosmic blueprint was slowly being inked in. Then, the universe entered a more dramatic phase, the non-linear collapse. As more and more matter streamed into the filaments, their gravitational pull intensified. They transitioned from being gentle slopes to becoming deep gravitational trenches. The flow of matter was no longer a slow drift, it became a rapid, channeled river. The filaments themselves became distinct and powerful, acting as cosmic highways that efficiently funneled gas and dark matter toward the intersections, the future homes of giant galaxy clusters. Supercomputer simulations show this process in stunning detail. We can watch as virtual filaments thicken and elongate over cosmic time. They are not passive strings, they are active conductors of matter. As the universe expands, these rivers stretch, but gravity constantly works to pull more material into them, causing them to densify and strengthen. The flow rate and density within these rivers are not constant. In the early universe, the currents were rich with pristine hydrogen and helium gas, a plentiful fuel supply for the first generations of stars. But as time passed, the nature of the flow changed. Some galaxies, caught in particularly dense and fast-moving currents, were flooded with fuel, triggering intense bursts of star formation. Others found themselves in quieter backwaters, their fuel supply dwindling as the cosmic rivers evolved around them. There is an even more violent process at work known as cosmic web stripping. Imagine a galaxy sailing through a dense filament. The pressure from the superheated gas flowing through that filament can be so immense that it acts like a torrential wind, physically tearing the galaxy's own gas reservoir away. This strips the galaxy of its future star-forming material, leaving it to fade away, a victim of the very river that once fed its ancestors. This dynamic evolution is the key to understanding the varied fates of galaxies. A galaxy's destiny, whether it becomes a brilliant spiral or a dormant red sphere, is largely a consequence of its position and movement within this flowing network. But how does this vast, impersonal flow of dark matter and hot gas actually connect to the birth of a single, shining star? A galaxy's brilliant core is a direct reflection of its supply lines. Think of a spiral galaxy like our own Milky Way not as an isolated island, but as a thriving metropolis whose entire economy depends on deliveries from an intricate network of invisible highways. The primary import is pristine hydrogen gas, the raw material for new stars, and the most efficient delivery system the universe has devised is a process known as cold flow accretion. This is how a galaxy gets its fuel directly from the cosmic rivers. Picture a river of cold, dense gas flowing smoothly along a dark matter filament. As this river approaches a galaxy's vast, diffuse halo of hot gas, something remarkable happens. Instead of crashing into this halo and heating to millions of degrees, the cold, narrow stream pierces right through it. It is like a deep underwater current moving through a warm surface layer, remaining intact and delivering its cold payload directly to the galactic disk. This direct fuel line is incredibly efficient. As cosmologist Dr. Avishai Deckel has emphasized, this cold mode accretion is the dominant mechanism for building massive, star-forming disks, especially in the early universe. The gas arrives cold and ready to collapse, providing a continuous supply of fuel that can trigger and sustain furious waves of star birth. This stands in stark contrast to its far less efficient counterpart, hot mode accretion. In that scenario, gas that is not channeled by a filament falls haphazardly onto a galaxy. It slams into the galactic halo at tremendous speed, creating a violent shock wave that heats the gas to extreme temperatures. This superheated gas must then cool down for millions of years before it can possibly collapse to form stars, a slow and inefficient process. The fate of a galaxy, therefore, is a tug-of-war between these two modes of fueling. A galaxy situated at the confluence of several strong cosmic filaments will be flooded by cold flows, leading to a rich, gas-filled existence and a high rate of star formation. We see this in the distant universe, where some of the most prolific star-bursting galaxies are found precisely at these busy intersections of the cosmic web. They are cosmic boomtowns, their growth exploding thanks to an abundant and direct supply of raw material. Yet this fueling process is not a simple one-way street. A galaxy is not just a passive recipient of this cosmic bounty. As stars are born, live, and die, they give back to the flow. Massive stars explode as supernova, and supermassive black holes at galactic centers erupt with energy, blasting winds of material and radiation back out into intergalactic space. This creates a complex feedback loop, a cycle of give and take between the galaxy and the vast rivers that sustain it. The galaxy consumes the fuel, but it also seeds the future flow with heavier elements forged in its stellar cores. A galaxy's brilliant life can reshape the very rivers that feed it. This is the principle of cosmic feedback, a self-regulating cycle where a city alters its own supply lines. The most dramatic agents of this change are the titanic outflows from supernova and the supermassive black holes at galactic centers. These events do not just happen within a galaxy, they blast material and energy back out into the vast intergalactic rivers, heating the gas, pushing it away, and fundamentally changing the local flow of the cosmic web. A galaxy can, in effect, build a dam against its own river. We see this in two primary forms. The first is stellar feedback. When massive, short-lived stars die in violent supernova explosions, they drive powerful winds. These winds blow colossal bubbles of hot gas out of the galactic disk, polluting the surrounding intergalactic medium with heavy elements like carbon, oxygen, and iron forged in stellar cores. This process is relatively localized, but it can effectively shut down star formation in a region by clearing away the very gas needed to make new stars. It is a regulatory mechanism that prevents a galaxy from burning through its fuel too quickly. The second, and far more potent, form of feedback comes from active galactic nuclei. When a supermassive black hole at a galaxy's core actively feeds on surrounding matter, it does not consume quietly. The infalling material releases a phenomenal amount of energy, powering jets and winds that can blast across hundreds of thousands of light years. This GN feedback can heat the vast reservoirs of gas in an entire galaxy cluster, preventing that gas from cooling and falling in to form new stars. In this way, a single black hole can put an entire metropolis on a diet, quenching future growth and leaving the galaxy to slowly redden and fade. Yet this feedback is not purely destructive. The same forces that can strip a galaxy of its gas can also, paradoxically, trigger new waves of creation. When a galactic wind slams into a slower moving cloud of gas in the halo or a filament, it can compress that cloud, causing it to collapse and ignite a firestorm of new star formation. It is the cosmic equivalent of a strong wind, not just extinguishing a fire, but blowing embers into a new patch of dry grass, starting fresh blazes elsewhere. This dynamic interplay between inflow and outflow, between construction and destruction, dictates a galaxy's ultimate personality. A delicate balance determines whether a galaxy will remain a vibrant blue star, forming spiral, or transition into a quiet red and dead elliptical. This grand cycle connects the smallest scales to the largest, but it raises a profound question about our own place in this flowing web. Two seeds, genetically identical, hold the same potential. Yet one lands in rich soil by a flowing river, while the other falls onto parched, barren ground. Their destinies will be nothing alike. This simple truth of nature applies on the grandest scale imaginable to the galaxies themselves. A galaxy's fate is not written in its stars, but in its cosmic zip code, its specific location within the flowing river system of the web. The environment a galaxy calls home dictates whether it will become a brilliant, star-forming spiral or a quiet, red and dead elliptical. This is the great divergence of galactic life. In the sparse, quiet voids, far from the strong currents of the filaments, galaxies are isolated. They are like remote homesteads with limited supplies. They slowly consume their internal gas reserves, forming stars at a leisurely pace until their fuel is gone. Their growth is stunted not by violence but by simple scarcity. They are the cosmic deserts. At the other extreme are the dense, chaotic environments at the confluences of rivers, the great galaxy clusters. Here, galaxies are like ships caught in a crowded, turbulent harbor. They experience a brutal process known as environmental quenching, where their life-giving gas is violently stripped away. One primary mechanism is ram pressure stripping. As a galaxy moves at tremendous speed through the superheated plasma that fills a cluster, the interstellar pressure feels like a hurricane-force wind. This wind can literally blow the galaxy's own gas reservoir out into space, robbing it of the raw material for new stars. The galaxy is starved into quiescence. Another destructive force is tidal stripping. The immense gravitational pull from the cluster and from near misses with other galaxies can stretch and distort a galaxy, pulling its stars and gas out into long, streaming tails. A third process is galaxy harassment, the cumulative effect of countless small gravitational tugs from neighbors, which can puff up a spiral disk into a featureless spheroid. These relentless forces in dense environments efficiently transform vibrant spiral galaxies into red and dead ellipticals. The evidence for this environmental dependence is overwhelming. Massive galaxy surveys like the Gamma project have meticulously mapped the properties of hundreds of thousands of galaxies. They reveal a stark and clear correlation. In the dense urban centers of galaxy clusters, red, elliptical galaxies dominate the population. But as you move out into the quieter suburban filaments, the number of blue, star-forming spiral galaxies steadily increases. The data paints a direct line from a galaxy's local density in the cosmic web to its color, shape, and very life force. So the question becomes, can we witness this fateful interaction as it happens? The evidence for these cosmic supply lines is written in the faintest light. Astronomers act as detectives, searching for the subtle clues that a galaxy is actively being fed by an invisible river. Their most powerful tool is a technique called absorption line spectroscopy. It works by using the universe's brightest beacons, quasars, as cosmic flashlights. As the intense, pure light from a distant quasar travels billions of light years to reach our telescopes, it passes through the extended halos of foreground galaxies and the very filaments that feed them. If there are clouds of cool, dense gas along that path, they will absorb very specific wavelengths of the quasar's light. Each element, like hydrogen or oxygen, leaves a unique fingerprint, a dark line in the otherwise smooth spectrum. By analyzing the pattern, depth, and position of these absorption lines, astronomers can determine the composition, density, and most importantly, the motion of the gas. When they see these lines shifted toward the blue end of the spectrum, it indicates the gas is moving toward us, a telltale signature of infall, of gas raining down onto the galaxy from a cosmic stream. Instruments like the Cosmic Origin Spectrograph on the Hubble Space Telescope have become masters of this art, revealing a vast population of these gas clouds around galaxies, their motion perfectly consistent with the predicted cold flows. But the clues do not stop there. A galaxy that has recently received a fresh delivery of gas from a specific direction often shows its history in its structure. Many spiral galaxies display a lopsided distribution of gas in their outer halos, a heavy concentration on one side. This is the cosmic equivalent of a pile of unopened packages stacked by the front door, a clear sign of a recent directional accretion event. An even more dramatic signature is a counter-rotating gas disk. Imagine a galaxy where the vast majority of stars and gas rotate in one direction, but a small, inner disk of gas spins the opposite way. This is a glaring inconsistency that can only be explained by a recent merger or the capture of gas from a filament that was orbiting in the opposite direction. It is a fossil record of a past encounter with a cosmic river. The ultimate goal is to see these rivers directly, while the cold, dark cores of the streams are nearly impossible to spot. Astronomers have begun to capture their luminous counterparts. Around some incredibly active, high-redshift galaxies, they have spotted faint, glowing filaments of gas. These are the streams lighting up, not from their own internal light, but from the intense radiation of the prolific star formation they are fueling. It is like seeing a river at night, illuminated only by the city lights it flows past. These observations are incredibly difficult, pushing our telescopes to their absolute limits, but they provide the most direct visual confirmation that the theoretical rivers are real. Despite these breakthroughs, profound mysteries linger, especially around the most massive galaxy clusters in the universe. Our models suggest these colossal structures should be fed by the mightiest rivers of all, yet the observational evidence for these grandest of flows remains elusive. Are they there, but simply too faint or too diffuse for our current instruments to see? Or is there something fundamentally different about how matter flows into the universe's most extreme environments? The hunt for these final pieces of the puzzle continues, driving the development of the next generation of telescopes that will peer even deeper into the cosmic currents. The mightiest cosmic rivers converge at the nexus of galaxy clusters. These are the superhighway interchanges of the universe, where multiple dark matter filaments meet, creating a gravitational well of unimaginable depth. All the gas flowing along these vast channels is funneled directly into the cluster's heart, building the largest structures gravity can hold together. To understand the sheer scale of this inflow, we turn to X-ray vision. Space telescopes like Chandra do not see the dark, starry galaxies in a cluster. Instead, they see the true monster, a colossal atmosphere of superheated plasma that glows brilliantly in X-rays. This gas is not merely a cloud, it is the cluster's primary component, a seething ocean of matter that contains far more material than all the galaxies combined. And this ocean is constantly being replenished by the rivers of the cosmic web. The process that builds these behemoths is called hierarchical clustering. It is a cosmic assembly line that operates over billions of years. Smaller groups of galaxies, themselves fed by smaller filaments, flow along the major intergalactic highways. They are like tributaries merging into a great river, all moving toward the same deep gravitational basin. When these groups reach the cluster, they do not simply join quietly. They merge, their gas colliding and heating to even more extreme temperatures in a violent, chaotic dance that adds both mass and energy to the growing giant. At the very center of many clusters lies a fascinating puzzle, a region known as a cool core. Here, the gas is so incredibly dense that it should radiate its heat away rapidly, cooling down and collapsing in a torrent of new star formation. This cooling flow should create a storm of stellar birth, yet we often see it mysteriously suppressed. The culprit is the supermassive black hole at the center of the cluster's central galaxy. As gas begins to cool and fall toward this black hole, it fuels an explosive outburst. The black hole erupts, pumping vast amounts of energy back into the surrounding gas, reheating it and preventing further cooling. This creates a delicate, self-regulating feedback loop, a balance between the relentless inflow of cold gas and the explosive output of the central engine, which prevents the cluster core from burning out too quickly. These clusters are not the end of the line. They themselves are the building blocks for the next level of cosmic structure, the superclusters. These are not gravitationally bound, but are immense tendrils of clusters and filaments, forming the grandest patterns in the universe, great walls of galaxies spanning hundreds of millions of light years. The flow of these cosmic rivers, from the faintest thread to the most massive cluster, charts the entire life cycle of cosmic evolution, a story written in the invisible currents of dark matter and the fiery glow of trapped gas. Far from the bustling cosmic highways, entire galaxies drift in profound solitude. These are the void galaxies, isolated islands adrift in the immense, empty oceans of space known as cosmic voids. These voids are not just empty patches, they are the dominant feature of our universe, occupying most of its volume. While the cosmic web's filaments are dense with traffic, the voids are realms of stunning emptiness, where galaxies are cut off from the nourishing rivers of gas. The result is a starkly different kind of evolution. Freed from the violent tides and relentless pressures of crowded clusters, void galaxies live quiet, isolated lives. Surveys dedicated to this population, like the Void Galaxy Survey, reveal them to be often smaller, bluer, and more irregular in shape than their cousins in the dense filaments. They are cosmic fossils, preserving a purer record of how a galaxy evolves when left almost entirely to its own devices. This isolation leads to a crucial cosmic debate, the question of nature versus nurture on a galactic scale. For a galaxy in a dense cluster, its fate is shaped by nurture, by a violent environment of mergers and stripping that forces it to change. But a void galaxy is a testament to nature. It evolves based almost solely on its own internal processes, a slow and gentle aging largely untouched by the chaos of the outside world. Because they experience far fewer galactic collisions and mergers, they avoid the dramatic transformations that turn spirals into ellipticals. Their gas reservoirs remain mostly intact, allowing for steady, if slow, star formation that often gives them a bluer, younger appearance. They are the universe's independent homesteaders, living off their own land without outside trade. Detecting the trace amounts of gas within these voids is one of astronomy's great challenges. The intergalactic medium here is even more diffuse than in the filaments, a faint and pristine relic of the early universe. This gas may represent a more primordial phase, never heated by the shock waves and fierce radiation that floods the cosmic web. Finding it is like trying to hear a whisper in a silent cathedral. The signal is incredibly faint, but it holds secrets about the raw material of the cosmos before any structure formed. The very existence of these two radically different environments, the dense filaments and the empty voids, and the distinct galaxies they produce, is a triumphant validation of the cosmic web model. It proves that a galaxy's destiny is inextricably linked to its address in the cosmos. This grand theory, which so accurately predicts the fate of galaxies from the richest clusters to the loneliest voids, did not spring from a single moment of discovery, but was woven together over decades by visionary minds. The cosmic web was first mapped not with a telescope but with mathematics. In the 1970s, decades before our most powerful supercomputers, a Soviet physicist named Yakov Zeldovich performed a breathtaking feat of prediction. He started with the initial conditions of the universe, the faint quantum ripples from the Big Bang, and asked a simple question: how would gravity sculpt these ripples over billions of years? His calculations, known as the Zeldovich approximation, revealed that the universe would not collapse into spheres or random clumps. Instead, it would naturally form a web. Matter would first collapse into vast, two-dimensional sheets, which he called pancakes. These sheets would then crinkle and stretch, with matter flowing along their intersections to form the dense, one-dimensional filaments we now know as the backbone of the cosmos. Zeldovich, with pen and paper, had seen the invisible rivers long before we had any proof they existed. For years, this was a beautiful but unproven theory. The breakthrough that turned his vision into a virtual reality was the development of n-body simulations. In the 1980s and 90s, scientists gained the computational power to model the universe as a collection of millions and then billions of particles interacting only through gravity. They would set these virtual particles in motion based on the early universe's conditions. Press play and watch. The result was astonishing. As the simulation ran, the particles did not just form a uniform haze. They coalesced along clear, distinct lines, tracing out a cosmic web of filaments and voids that mirrored Zeldovich's predictions with stunning accuracy. These were the first digital maps of the dark matter rivers, confirming that gravity alone was enough to weave the largest structure in the universe. The story did not end with dark matter. The next great leap was to populate these dark skeletons with the stuff of stars and galaxies. This required hydrodynamical simulations like Illustris and Eagle. These models are vastly more complex, adding the physics of superheated gas, the ignition of stars, and the explosive feedback from supernova and black holes. They simulate not just where the dark matter flows, but how the ordinary matter follows, how it cools, and how it eventually lights up to form the galaxies we see. These virtual universes made specific, testable predictions. They told us that filaments should have typical densities, specific lengths stretching tens of millions of light years, and that they should contain a precise fraction of the universe's total mass. They predicted the existence of the warm-hot intergalactic medium, the WIM, flowing within them. Every one of these predictions has become a target for observers, a set of clues that astronomers now hunt for in the real sky. Yet for all their power, these models face profound challenges, simulating the intricate dance between gas and dark matter, between the constructive force of gravity and the destructive fury of black hole feedback, pushes our most powerful computers to their limits. The models sometimes struggle to create galaxies of the right size and shape, or to perfectly balance the rate of star formation. These are not failures but frontiers. Each discrepancy is a signpost pointing to a piece of physics we have yet to fully understand, a reminder that the final map of the cosmic rivers is still being drawn. Our current map of the cosmic web resembles a medieval chart with known coastlines and vast, blank areas marked by the unknown. We have traced the dark matter skeleton and glimpsed the fiery glow of the WHIM, but significant portions of this cosmic river system remain stubbornly unmapped. Primary challenge is the very nature of the warm-hot intergalactic medium itself. This gas is so diffuse and so hot that it barely interacts with light, making it nearly transparent to our telescopes. This is the heart of the missing baryons problem, a cosmic accounting error where a substantial fraction of the universe's ordinary matter has simply evaded direct detection. We know it must be there, woven through the filaments, but capturing its faint signal is like trying to photograph a whisper. Our theoretical models face their own hurdles. The supercomputer simulations that so beautifully predict the cosmic web's large-scale structure are limited by their resolution. They can show us the grand flow of a dark matter river, but they cannot yet zoom in to model the small-scale chaos within. The intricate physics of how gas cools, how turbulence stirs it, and how magnetic fields might shape it within these filaments happens on scales too fine for our current virtual universes to capture. It is the difference between mapping a continent's major river systems and understanding the complex whirlpools and eddies around every single rock. Closer to home, a more mundane obstacle blocks our view, the dust and stars of our own Milky Way. This creates a zone of avoidance, a blind spot in our cosmic maps that obscures a significant portion of the sky. We are like cartographers trying to map the world while standing in a dense forest, unable to see the horizons our models tell us must be there. Compounding this is the profound challenge of cosmic variance. We have only one universe to observe. This makes it impossible to run a true experimental test on many of our statistical predictions about the web's structure. Are the filaments we see in our local patch truly representative of the cosmos as a whole, or are we living in a slightly unusual neighborhood? We have no other universe to compare it to. Yet these very challenges are the engines of astronomical progress. The missing baryons problem is the driving force behind a new generation of space telescopes and survey instruments designed specifically to hunt for the faintest signatures of these cosmic currents. The limitations of our simulations push computer scientists and physicists to develop more sophisticated codes and harness greater processing power. Each blank spot on our map is not a dead end, but a destination, a call for a new voyage of discovery into the final unseen frontiers of our universe. The next generation of cosmic cartography is already taking shape in laboratories and design studios around the world. These are not mere upgrades to our current tools. They are revolutionary instruments conceived for a single purpose: to finally see the unseen rivers in their full, flowing glory. They will act as a kind of cosmic sonar, sending out not sound but the most advanced forms of light and radio waves to illuminate the depths of the intergalactic void. At the forefront is the European Space Agency's Athena mission, the advanced telescope for high-energy astrophysics. Scheduled for launch in the next decade, Athena carries an X-ray spectrograph of such phenomenal precision it will be able to do what was once thought impossible. It will not just detect the warm, hot intergalactic medium, it will map its detailed structure and motion. By observing the faint fingerprints of highly ionized oxygen in the WHIM, Athena will trace the velocity and density of these gaseous currents across millions of light-years, transforming vague theoretical streams into a charted flow. This work will be complemented by other visionary projects. The proposed Lynx X-ray Observatory aims for even greater sensitivity, promising to see the faintest threads of the web. Meanwhile, on the ground, the Square Kilometre Array, or SKA, will use thousands of radio antennas to conduct a different kind of search. It will scan for the faint emission from neutral atomic hydrogen, the cooler, pristine gas that also flows along the filaments. This is the crucial synergy. Athena will map the hot, ionized plasma, while the SKI charts the cold, atomic fuel. Together, they will provide the first complete census of the cosmic river's contents, from its fiery surface to its cold, dark undercurrents. But these telescopes are only one part of the equation. To interpret the torrent of data they will send back, we need an equally revolutionary leap in our virtual universes. The next frontier is exascale computing, machines capable of performing a quintillion calculations per second. This raw power will allow cosmologists to run simulations with unprecedented resolution, modeling not just the broad sweep of a dark matter filament, but the complex turbulence and magnetic fields within the flowing gas itself. They will be able to watch in exquisite detail how a supernova shock wave propagates through the intergalactic medium, or how a black hole's jet disrupts an entire galactic inflow. Machine learning will supercharge this process, sifting through the immense observational datasets to find subtle patterns and correlations that would take human researchers a lifetime to uncover. These AI assistants will help us identify rare structures and predict where the most interesting cosmic currents might be found. The ultimate goal of this entire endeavor is far more profound than simply completing a map. The data from Athena, the SKA, and the exascale simulations will serve as a fundamental test of our physical laws on the largest scales imaginable. Does gravity behave exactly as Einstein predicted across these vast filamentary structures? Does the dark energy that drives the universe's acceleration interact with these rivers in any detectable way? By charting the real flow of matter against the predicted flow from our most sophisticated models, we are conducting an experiment on the universe itself. The journey to map the cosmic web is a quest to understand the fundamental rules that have shaped everything from the largest cluster to the smallest star. These silent rivers may hold the key to unlocking physics we cannot yet recreate on Earth. The cosmic web is more than a structure. It is a fundamental laboratory, one where the nature of dark matter and dark energy is written into the geometry of the streams themselves. Every detail of a filament, from its thickness to its texture, is a clue. The standard model of cosmology relies on what we call cold dark matter. This model assumes dark matter particles move slowly, allowing them to clump easily into the fine, intricate web of filaments we see in simulations. But what if dark matter were different? If dark matter were warm, meaning its particles moved at a significant fraction of light speed in the early universe, it would have washed out some of the smallest structures. The result would be a cosmic web with fewer threads, and the filaments that did form would be smoother and less defined, lacking the complex, knotted substructure predicted by the cold model. This gives astronomers a direct test. By counting the number of faint, dwarf galaxies that should trace the thinnest cosmic filaments, we can probe the particle nature of dark matter itself. A lack of these small, dim galaxies along the rivers would be a powerful indicator that dark matter is warm, fundamentally altering our understanding of its identity. The cosmic web also tests the very law that shapes it, gravity. Our standard model relies on Einstein's theory of general relativity operating on the largest scales. But some scientists propose modified theories like MOND, which change how gravity behaves in the weak fields found between galaxies. These alternative theories make specific predictions about how matter should flow into filaments and how those filaments should be arranged. A precise, three-dimensional map of the cosmic web's geometry, the angles at which filaments connect and their relative densities, acts as a ruling rod. Any significant deviation from the pattern predicted by standard gravity and dark matter would point toward a new, revolutionary law of physics. Perhaps the most profound connection is to the universe's accelerating expansion, driven by the mystery of dark energy. The growth of the cosmic web is a tug-of-war between the relentless pull of gravity, trying to build structure, and the outward push of dark energy, which works to tear it apart. By measuring how quickly the filaments have thickened and strengthened over cosmic time, from the distant past to the present day, we can measure the strength of dark energy's influence throughout history. A change in the growth rate of these rivers would tell us if dark energy is a constant force, as Einstein's cosmological constant suggests, or if its strength has been changing over billions of years. This turns the entire observable universe into an instrument for measuring its own ultimate fate. What begins as a quest to map the unseen currents that feed galaxies evolves into a deep interrogation of the cosmos's most basic rules. The destiny of galaxies and the nature of reality itself are flowing together in these same dark, silent streams. Our own galaxy is sailing on one of these vast, invisible rivers. The Milky Way is not a fixed landmark in the cosmos but a vessel in motion, carried by gravitational currents that flow through our local region of space. This journey is measured by what astronomers call our peculiar velocity, the difference between our galaxy's actual motion and the uniform expansion of the universe. We are not just drifting aimlessly, we are being pulled. The primary source of this pull is a mysterious region of immense gravity known as the Great Attractor, located in the direction of the Centaurus constellation, hundreds of millions of light years away. This is not a single object, but a gravitational focal point, the heart of our home supercluster, Laniakea. The name Laniakea means immense heaven in Hawaiian, and it is a fitting title for a structure that contains over 100,000 galaxies, all flowing toward a common center of gravity. Projects like the Cosmic Flows Survey, led by astronomer R. Brent Tully, have meticulously charted this motion. By measuring the distances and velocities of thousands of galaxies, they have created a dynamic map of our local universe, revealing the Milky Way as one leaf caught in a vast, slow-moving river, all of us streaming toward the same unseen destination. The river we ride is part of a local filament, a tendril of the cosmic web that connects larger structures. One significant local current links the Virgo cluster, a massive collection of galaxies, to our own local group, which contains the Milky Way and Andromeda. This filament is the local superhighway, a conduit of dark matter and diffuse gas that guides the motion of galaxies in our immediate neighborhood. Is this river still feeding us? The evidence suggests that while the grand, cold flows that built galaxies in the early universe have diminished, our galaxy continues to accrete gas. This incoming fuel is more subtle now, arriving as a gentle rain of high-velocity clouds or smaller, shredded gas clouds, likely stripped from dwarf galaxies or originating from the intergalactic medium itself. This trickle of new material is enough to sustain a modest rate of star formation, ensuring our galaxy remains a living, breathing entity. This local flow does more than just feed us, it dictates our ultimate fate. The same river that guides our path is also drawing our largest neighbor, the Andromeda Galaxy, closer to us. The impending merger between the Milky Way and Andromeda is not a random collision. It is a direct consequence of the shared gravitational well we inhabit within the Laniakea supercluster. Both of our galaxies are flowing down the same cosmic watershed, on a trajectory that will inevitably lead to a colossal union billions of years from now. This event will fundamentally reshape both galaxies, triggering a firestorm of new star birth and likely resulting in a new, giant elliptical galaxy. Our local context reveals a universe that is dynamic and deeply interconnected, where even the largest galaxies are subject to the silent, relentless pull of the cosmic currents. The diversity of river systems on Earth is mirrored perfectly in the cosmos. Just as our planet has everything from the vast, churning Amazon to a trickling mountain creek, the cosmic web contains filaments of every conceivable scale and strength. These rivers are not uniform conveyor belts, they are a spectrum of cosmic currents, each with its own personality and influence. The most massive filaments are the superhighways, colossal conduits that channel matter toward the universe's densest intersections, the great galaxy clusters. These are not simple threads, they are complex structures in their own right. Within these thickest rivers, cosmological simulations reveal entire embedded ecosystems. Smaller dark matter halos and whole groups of galaxies can travel along inside them, like barges and ships moving down a mighty continental river. This creates a nested hierarchy, rivers within rivers, all flowing toward the same gravitational sea. The power of these primary filaments directly dictates the destiny of the clusters they feed. A key factor is a cluster's connectivity, which is simply the number of thick, massive filaments that are plugged into it. Think of a city's economic power, determined by how many major highways and rail lines connect it to the wider world. A cluster fed by 3 or 4 powerful cosmic rivers will grow faster and become far more massive than a cluster at the end of a single, thinner filament. This connectivity is a primary driver of a cluster's ultimate size and richness. This cosmic watershed looks very different depending on when and where you observe it. In our local, modern universe, the web is relatively settled. The filaments are well-defined and stable, having finished their most dramatic growth billions of years ago. But if we look back in time to the high redshift universe, we see a far more chaotic and dynamic scene. The web back then was a rapidly assembling, frenetic network. Filaments were constantly forming, stretching, and merging, with matter flowing in violent, turbulent surges as the large-scale structure of the cosmos was being forged in fire. This comparative view is crucial. It reveals that the cosmic web is not a static sculpture but a living, evolving system. The type of filament a galaxy calls home, whether a stable, mature flow or a chaotic, young channel, leaves a permanent imprint on that galaxy's character, shaping its growth, its structure, and its very future. We are now in the age of cosmic cartography, building the ultimate three-dimensional atlas of the universe. This is not a single telescope's project but a global campaign, a race to map the sprawling river system of the cosmic web across billions of light years. At the forefront is the Dark Energy Spectroscopic Instrument, known as DESI. Perched atop a telescope in Arizona, DESI is an engineering marvel, a robot that can position 5,000 tiny fibers with hair's breadth precision. Each fiber captures the light of a single galaxy or quasar, measuring its redshift to pinpoint its distance. The goal is staggering: to chart the precise three-dimensional positions of 40 million galaxies and quasars. This will be the largest map of the universe ever created, a census of cosmic metropolitan areas that will trace the dark matter filaments in unprecedented detail. As a scientist from the DESI collaboration might explain, this map is not just a picture. It is a rich dataset that allows us to measure the statistical properties of the cosmic web. We can measure the typical distance between filaments, their thickness, and how these properties change over cosmic time. But how do you get from a map of glowing galaxies to a map of invisible dark matter? The galaxies are the tracers. Think of a city seen at night from an airplane. You cannot see the roads directly, but you can infer the entire highway network from the bright clusters of light and the glowing lines of towns connected by suburbs. In the same way, galaxies are not randomly scattered. They trace out the underlying dark matter skeleton because that is where gravity pulled them together in the first place. With tens of millions of precise galactic coordinates, the faint outline of the dark rivers emerges from the statistical noise. There is an even more powerful technique called Reconstruction. It uses the measured motions of galaxies to rewind the cosmic tape. Galaxies are not perfectly still on the cosmic web. They are flowing along the filaments toward the densest clusters, like leaves caught in a river current. By analyzing these subtle flows, astronomers can use sophisticated computer algorithms to sharpen the image. It is like taking a blurry photograph and using software to enhance the edges, turning a vague suggestion of structure into a clear, detailed map of the web's filaments and voids. DESI is not working alone. In space, the Euclid telescope is conducting its own vast survey, using a different technique to achieve a similar goal. And soon, the Vera C. Rubin Observatory's legacy survey of space and time will begin, a 10-year project that will image the entire southern sky every few nights. The LSST will not measure distances for as many galaxies as DESI, but it will detect billions of them, providing an unparalleled view of the web's two-dimensional projection and discovering countless rare cosmic structures for further study. Together, these projects are providing the raw material for the next great discoveries. This flood of data is more than just a map. It is a dynamic record of the universe's growth and a testing ground for our most fundamental physical laws. The true revelation may not be the map we expect to see, but the strange and unexpected structure we find hidden within the data. Every great exploration uncovers mysteries it never set out to find. The cosmic web, as we begin to trace its contours, is revealing profound puzzles that challenge our most basic assumptions about how the universe operates. One of the most stunning revelations has come from radio astronomers listening to the whispers of space. Using vast networks of antennas like the LOFAR telescope, they have detected extremely faint, diffuse radio emissions emanating from the hearts of the largest filaments. This radio glow is a signature of magnetic fields woven through the emptiness between galaxies. This is deeply puzzling. We thought magnetic fields were generated by the dynamo action within galaxies, churned by the motion of spinning stars and gas. Finding these fields far out in the void, far from any obvious source, forces us to reconsider their cosmic origins. Perhaps they were seeded in the universe's earliest moments and stretched to immense scales by the expansion of space, or maybe there are unknown processes, turbulent flows within the filaments themselves that can amplify these fields. Either way, it is a clear signal that we are missing a fundamental piece of physics. The surprises do not stop with magnetism. Our census of the cosmic rivers has turned up a strange population of dwarf galaxies. There seem to be more of these small, faint galaxies lining the filaments than our best supercomputer simulations predict. It is as if our virtual universes are missing an entire class of citizen in the cosmic metropolis. This discrepancy is a direct clue to the nature of dark matter. If our standard model of cold dark matter is correct, it should predict the right number of these small halos. Their overabundance suggests that dark matter might behave in more complex ways than we thought, or that our understanding of how gas cools and forms stars in these tiny systems is fundamentally incomplete. This leads to an even more ghostly possibility. Could these filaments be haunted by dark galaxies? These would be halos of dark matter that gathered in the early universe but for some reason failed to pull in enough ordinary gas to ignite star formation. They would be invisible, made almost entirely of dark matter, drifting like ghost ships in the cosmic currents. Their predicted existence is a direct consequence of our models, but finding them is one of astronomy's greatest challenges. Further complicating the picture is the unexpected chill within the streams. While we call it the warm-hot intergalactic medium, astronomers have also spotted patches of gas within filaments that are significantly cooler than the models allow. This gas should be heated to millions of degrees by the shock waves of cosmic structure formation, yet some of it remains surprisingly cold and dense. This cool gas could be a remnant of the pristine early universe, or it might indicate that our models are oversimplifying how energy is distributed through these vast structures. Each of these puzzles, from the magnetic fields to the surplus dwarfs and the cool gas, is a gift. They are not failures of our theories, but signposts pointing toward a richer, more complex reality. They remind us that the universe is always more inventive than we are, and that the final chapter on the cosmic web is far from written. This intricate cosmic architecture transcends its scientific function, revealing a pattern of breathtaking beauty. The filaments and voids of the cosmic web form a masterpiece on the grandest possible canvas, a structure that resonates with a deep, almost intuitive sense of order. It is a universal pattern, a fundamental geometry that repeats itself throughout nature. Look closely at a single neuron in the human brain, with its delicate branches reaching out to form connections. Then pull back to see the cosmic web, with its galaxies linked by flowing tendrils of dark matter. The resemblance is not a mere coincidence. It is a hint that the same underlying principles of network formation, of optimizing connections and flows, might govern systems from the microscopic to the cosmic. This pattern appears again in the intricate mycelial networks of fungi beneath the forest floor, another hidden web sustaining life above. Artists and philosophers have long been drawn to these cosmic visualizations. They see in them more than just data. They see a map of existence itself. The images evoke a powerful sense of connectedness, a visceral understanding that everything from the atoms in our bodies to the most distant galaxy is part of a single, flowing entity. It is a beauty that is both humbling and exhilarating, shrinking our individual concerns while simultaneously making us feel part of something immense and eternal. The visualizations themselves, often glowing renderings from supercomputer simulations, have become the iconic art of our scientific age. They are not photographs, but they are profoundly real, translating the invisible gravitational currents into a language of light and form that our minds can grasp. These images bridge the gap between abstract theory and public imagination, allowing everyone to witness the hidden architecture of our universe. This connection has become tangible through citizen science projects like Galaxy Zoo, where hundreds of thousands of volunteers have helped astronomers classify the shapes of millions of galaxies. By looking at these images and making simple classifications, people around the world are directly participating in the mapping of the cosmic web. They are not just learning about the structure, they are helping to trace its lines with their own eyes, fostering a personal relationship with the cosmos. To gaze upon this grand design is to be invited to ponder an ultimate question. What will become of this magnificent, flowing network as the eons stretch onward? The same cosmic rivers that built our galactic home will one day carry it toward oblivion. The universe is not in a steady state. It is a story with a final chapter, and the plot is driven by a mysterious force known as dark energy. This invisible pressure, woven into the fabric of space itself, is causing the expansion of the universe to accelerate. For billions of years, gravity has been the dominant sculptor, tirelessly pulling matter into filaments and clusters. But in the grand cosmic timeline, we may be living in a brief golden age, a window where gravity's work is nearly complete, but dark energy has not yet fully asserted its destructive power. Theoretical models project a future where this acceleration does not just continue, it wins. In one possible scenario, the Big Rip, dark energy grows so strong that it overwhelms every force that holds things together. First, it would tear galaxy clusters from one another, severing the thickest filaments of the cosmic web. Then, the gravitational bonds within individual galaxies would fail, sending stars flying off into the expanding darkness. Finally, planets, molecules, and even atoms themselves would be ripped apart. It is a future of ultimate isolation, where the very concept of a river or a web becomes meaningless. But this dramatic end is not the only possibility. A more gradual, though equally final, fate is heat death. In this scenario, the expansion continues at a less violent pace, but with the same desolate outcome. The flow of gas along the filaments will first slow to a trickle and then stop entirely. Galaxy clusters will become isolated islands, their connections to the wider web stretched and broken. The universe will grow vast, cold, and dark, with the last stars flickering out as their fuel is exhausted. The great rivers of dark matter and gas will thin into a featureless, ever-expanding haze. Yet this ultimate dissolution is still tens of billions of years away. In the more immediate cosmic future, the web's activity will continue. For many billions of years to come, gravity will still rule locally. Galaxy groups will continue to stream along the filaments, merging to build ever larger clusters. The Milky Way and Andromeda will collide and merge, a spectacular but local event in this ongoing construction. The cosmic web will appear to thrive, even as the foundation of space itself is shifting beneath it. This long-term view forces a profound perspective. The brilliant, dynamic cosmic web we see today is not permanent. It is a fleeting structure, a magnificent but temporary pattern in the cosmic tapestry. Its existence, from the first quantum ripple to its final silent unraveling, is a single, grand narrative of emergence and dissolution. To understand its flow is to grasp not only how we came to be, but the ultimate context for everything we see in the night sky. A galaxy's story is not written in isolation. It is a biography authored by the river it calls home. We now understand that galactic evolution is a symphony conducted by the cosmic web, a unified process where a galaxy's mass, its history of collisions, and its continuous dialogue with the invisible currents all combine to write its final chapter. This is a profound paradigm shift. We have moved from seeing galaxies as island universes to recognizing them as deeply interconnected inhabitants of a flowing cosmic ecosystem. Their properties are not set at birth but are forged through a lifetime of interactions. The life cycle begins with a collapse within a dark matter halo, a gravitational well carved by the web's initial architecture. This young protogalaxy is then sustained for billions of years by cold, narrow streams of gas flowing directly from the cosmic filaments, a direct fuel line that allows it to build a brilliant disk of stars. But this growth is not guaranteed. Its fate can be dramatically altered by its environment. A galaxy sailing into a dense cluster may have its gas stripped away by the immense pressure of the intercluster plasma, quenching its star formation in a process called ram pressure stripping. Alternatively, its own internal processes can dictate its maturity. The furious energy from supernova and a central supermassive black hole can blast its gas reservoirs back into the void, a self-regulating feedback loop that prevents it from burning too brightly, too fast. This synthesized picture elegantly explains the grand patterns we observe across the cosmos. It is the reason we see the morphology-density relation, where dense urban centers of galaxy clusters are dominated by red, dead ellipticals, while the quieter suburban filaments host vibrant, blue, spiral galaxies. It accounts for the star-forming main sequence, the clear relationship between a galaxy's mass and its rate of making new stars, a balance set by the efficiency of its cosmic supply lines. Charting these unseen rivers is therefore fundamental. It is the key to understanding why our universe looks the way it does, from the loneliest void galaxy to the brightest cluster core. Every thread of our journey converges here on a single, powerful realization. We are not just mapping the cosmos, we are reading the story of its interconnected life.